141. Find the minimum time to reach last room 1. So to solve this problem, we need to know two concepts, heaps and Dijkstra's algorithm. So heaps are basically what you see here. It's a binary tree where the root is always going to be the largest or minimum most value of its relative to its children. So notice how 10 is larger than all the elements below it. 5 is larger than all the elements of its children. So that's the idea. We're always going to have the largest value or the minimum most value at the root right here. And for Python, by default, it's going to be the minimum most value. And for Dijkstra's algorithm, it's an algorithm that finds you the shortest path within a graph. And it does this with BFS, where you basically expand from one node to its adjacent neighbors, trying to basically find the path with the lowest cost. And we'll see this in action with the following example. The goal is to go from here to here by only traversing through adjacent nodes. And by definition of adjacent, it's up, down, left, or right. So with this, what can we say? How do we go from 3 to 103? Well, at every single node, we have one of 4 options, right? We can go in one of 4 directions. So in this case, we go from t is equal to 0, and basically go all the way to 103. Now one of the criteria is that you can only move to each node if the time is okay, and that means that you can only go to this node when time is 1, and traversing between nodes takes another time of 1. Well, when we start at a given node, it doesn't really matter what it is, right? Because no matter what it is, it's not going to cost us any time to start at this node. So even though we start at 3, we default this to 0. So we can either go right or it can go down. If we go right versus going down, we're going to take a much less of a cost. It's only going to take us a cost of 1 versus a cost of 100. So we obviously want to go to 1. At node 1, we have one of 2 options. We can go here, or we can go here. Now, if we want to go down, then it's going to cost us a cost of 2. If we go to the right, it's going to take a cost of 4. Obviously, we're going to go down. And from 2, we're going to expand. We can either go left, right, down, right? And if we go left, that's obviously bad. If we go down, that's even worse, and we can only go right. So now we're at 3. And now that we're at 3, we can either go up or down. If we go down, we take 103, which is the objective, meaning we only have really one choice. Even though it's a much larger cost than 4, that is the objective node that we're trying to reach, so we go down. So what this basically means is that we always expand the node at which the minimum cost is currently available. And by doing so, we're always going to guarantee that we're traversing a path that has the lowest cost. In our case, it looks something like this. And with this, we can program it in Python. Alright, let's program this up. So to do this, as we said, we're going to be needing a 2D array to store the minimum times it takes to get to each node. And let's call this array min times. But min times have to have the same dimensions as move time. Well, the number of rows in move time is n, which is going to be the length of move time. M is going to be the length of move time of the 0th element, because it's going to be a list of lists. So min times is going to be what? Well, it stores the minimum times. So we always update min times from large times, which in our case it begins at infinite. So float inf times number of columns 4 underscore in range of the number of rows. With this, what else can we say? We also know we're going to need a heap. And we're going to do that by importing heap q. Now, the reason why we need a heap is because of the logic of how we always expand from the node that currently has the smallest time traversal. The heap always maintains which node currently has the smallest time to get there. And so we always expand from there because we're trying to always find the min path. Therefore, we're going to say min heap is going to be equal to an array. Heaps are represented as arrays within Python. And at the very beginning, we're going to push, right? So heap q dot heap push to min heap. What? We're going to push in 0, 0, 0. It's a tuple. And the tuple represents what? It represents the time, the x position, and the y position. In the tuple, the first value always has to be the priority. In our case, it's going to be the time, hence what we have here. And what else can we do? We also know that it doesn't matter what the first value in the 0th position is. It's always going to be 0 because it takes no time to start at that node. So while min heap is not empty, it means we have nodes to traverse. Hence, we're going to keep going until we reach what? Until we reach a destination. How do we know if we're at a destination? Well, the current time, the current x position, and the current y position is found by basically popping the current value from the heap. And if that position is equal to n minus 1 for x, and y is equal to n minus 1, we have reached a destination, so we should return it. It's in particular the time it took to get there. Otherwise, what can we say? If the current time is less than the min time it takes to get to the current node, it means we found a shorter path to get to this node. Therefore, we have to update the min time it takes to get to the current position to the current time, and we have to expand from the current node to find the next node to traverse in this minimum path. But what directions can we choose from? Well, we have one of 4 options. We can either go up, which is going to be 1, 0. We can either go down, negative 1, 0. We can go to the right, 0, 1. Or we can go to the left, 0, negative 1. So for dx, dy in directions, x new is going to be dx plus x, and the new y coordinate is dy plus y. And if this new coordinate, xn, is within the bounds of the 2D array, and the same goes for the new y position, and the node that we're trying to go to is an unexplored node, which is going to be denoted by min times of x new and y new being a float of infinite, then we can go to that node, and we have to push it into the heap to denote that we're going to traverse it next. And it's going to sort it automatically by min time. So we always know that we're always on the path of the shortest path. So the new time is going to be what? It's going to be equal to the max of the current time with the time at, I think it's move, what is it called? Move time. At the time of the new node, so xn, yn, plus 1. Plus 1 is because it takes a unit of 1 time to traverse an edge, and the maximum of this is because, let's say the current time is greater than the time it takes to go to the next node, like 5 and 3. Then we don't have to wait. We can just go there directly, and it doesn't take any waiting, so we just take the current time plus 1. Vice versa, we have to wait a number of units of time before we can reach it, and then plus 1 to get to that node. With this, we can push it into our heap. So we do heap q dot heap push into the min heap with new time xn yn. And with that, we should be good. That is the entire algorithm. So once we're done running the whole while loop, we return -1. We have to do this because there has to be a return statement, and in the event this all fails, it means we have to return -1. But this will never be returned. It's just for the sake of letting it pass. So let's run it. And min time is not defined. Oh, let's just do that. Let's do it again. Let's see. It's just a naming issue, so we're just gonna do min time. Boom. Right. Let's min time. We're gonna do this. We're going to do everything should be good now. Let's run it. Oop. And that works. So let's submit. And it works. That's the solution.